Introduction to Marginality in Economics. Hello, everyone. Let's begin our lesson on the economic applications of calculus. We will start with Slide 1, which introduces the concept of marginality. First, let's look at what marginal actually means in a business context. In the study of economics, the term marginal refers to the additional or incremental change that occurs when one more unit of a commodity is produced or consumed. Essentially, it is the cost or benefit of producing just one more item. Now, to bridge the gap between economics and mathematics, we can say that this incremental change is equivalent to the instantaneous rate of change of a function. If you recall from your calculus lessons, the instantaneous rate of change is the core definition of a derivative. Therefore, when we apply the concept of derivatives to economics, we can determine exactly how a total value, such as the total cost or total revenue, changes as the quantity of production changes. This sets the stage for the rest of our lesson, where we will move from this general theory to the specific calculation of marginal cost. Defining marginal cost, MC. Now that we have established the general concept of marginality as an incremental change, let's apply this specifically to the cost of production. First, let's look at the total cost, which we denote as C of X. This represents the total expense a company incurs to produce X units of a specific product. It is important to understand that this total cost is usually composed of two elements: fixed costs, such as rent, which do not change regardless of output, and variable costs, such as raw materials, which fluctuate based on the volume of production. Next, we define the marginal cost, or MC. In economic terms, this is the rate of change of the total cost with respect to the number of units produced. To put this in simpler terms, the marginal cost is essentially the approximate cost of producing one additional unit of a product. Mathematically, if we are given the cost function C of X, the marginal cost is the first derivative of C of X with respect to X. We express this formula as marginal cost equals dC over dx. In the following slides, we will explore how to interpret this derivative in a real-world scenario and walk through the steps to calculate it. Understanding the concept. Now that we have established the basic definition, let us break down the concept of marginal cost to ensure a clear understanding. First, consider the total cost, represented by the function C of X. This simply refers to the overall expenditure a company incurs to produce a specific quantity, X, of items. Next, we look at the derivative, denoted as dC over dx. As we discussed in the previous slide, this mathematical operation tells us the instantaneous rate of change, essentially, how rapidly the total cost is increasing as the number of units produced, X, increases. Finally, let us look at the economic interpretation of this value to see why this matters in the real world. For example, if the marginal cost at X equals 100 is $50, this implies that producing the 101st unit will cost the company approximately $50. Once you grasp this conceptual link between the derivative and the cost of the next unit, you will be ready to move on to the actual calculation process, which we will cover in the next slide. Step-by-step process to calculate marginal cost. Now that we have established the theoretical definition of marginal cost, let's walk through the practical process of how to calculate it. To find the marginal cost for any given production level, you should follow these 4 systematic steps. First, you must identify the cost function. This means obtaining the specific mathematical expression, which we denote as C of X, that represents the total cost of production. Second, you need to differentiate the function. By applying the standard rules of differentiation that we've studied in calculus, you will find the derivative of C with respect to X as we discussed in the previous slides. This derivative is the mathematical equivalent of the marginal cost. Third, you will substitute the value of X if the problem asks you to find the marginal cost at a specific production level. For instance, if X equals 10, You simply plug that number into the derivative formula you just created. Finally, you must interpret the result. It is important to remember that the final value you calculate represents the approximate cost of producing the next immediate unit of the product. To help you visualize this process, we will now move on to an illustrative example where we apply these steps to a real-world scenario. Illustrative example. Now that we have established the theoretical framework and the step-by-step process for calculating marginal cost, let us apply these concepts to a practical scenario. Consider a company that specializes in the production of high-end wireless headphones. To analyze their expenses, we are given a total cost function, denoted as C of X, which represents the total cost of producing X units of these headphones. The mathematical expression for this cost is C of X equals 5,000 plus 100X plus 0.5X squared. In this equation, the 5,000 represents the fixed costs we discussed earlier, while the remaining terms account for the variable costs. Our specific objective for this example is to find the marginal cost at the moment the company is producing 100 units. As we learned in the previous slides, this will tell us the approximate cost of producing the 101st unit. Let us now move to the next slide to solve this step-by-step. Step-by-step solution. Now, let's walk through the step-by-step solution for the wireless headphones scenario we introduced in the previous slide. Starting with step 1, we must first identify the cost function provided in the problem. In this case, the total cost, denoted as C of X, is equal to 5,000 plus 100X plus 0.5X squared. Moving to step 2, we need to find the marginal cost. As we established earlier, the marginal cost is the first derivative of the total cost function with respect to X. To achieve this, we will apply the power rule of differentiation, which states that the derivative of X raised to the power of n is equal to n times X raised to the power of n minus 1. Let's apply this rule to our specific function. We take the derivative of the entire expression, 5,000 plus 100X plus 0.5X squared. To make this simpler, we can differentiate each term individually. First, the derivative of the constant 5,000 is 0, as fixed costs do not change with production. Second, the derivative of 100x is simply 100. Finally, for the term 0.5x squared, we bring the exponent 2 down to multiply with 0.5 and reduce the power by 1, which gives us 1x. When we combine these results, our formula for marginal cost simplifies to 100 plus x. Now we proceed to step 3. The problem asks us to find the marginal cost specifically when 100 units are being produced. Therefore, we substitute the value of 100 for x in our marginal cost formula. This gives us 100 plus 100, which results in a final value of 200. In the next slide, we will discuss what this numerical result actually means for the company's production costs. Final interpretation. Now that we have completed the mathematical calculations in the previous slide, let us focus on what this result actually means in a real-world business context. We found that the marginal cost at a production level of 100 units is $200. In practical terms, this tells us that the cost of producing the 101st unit is approximately $200. This brings us back to the fundamental definition we discussed at the beginning of this lesson. The marginal cost is not the average cost of all units, but specifically the incremental cost of producing one more unit. With this interpretation clear, we can now move forward to summarize the key takeaways of this topic. Key takeaways. Now that we have worked through the practical example, let us summarize the key takeaways to ensure you have a solid grasp of the concept. First, please remember that in the context of economics, the word marginal is essentially a keyword for derivative. Whenever you encounter the term marginal in a problem, it is a direct signal that you need to find the derivative of the associated function to determine the instantaneous rate of change. To express this as a mathematical formula, marginal cost is equal to the derivative of c with respect to x. This formula is the foundation of the calculations we performed in the previous slides. You might wonder why this is so important in the real world. The primary purpose of calculating marginal cost is to help businesses decide whether increasing their production is financially viable. By knowing the cost of producing one additional unit, a company can determine if the extra revenue generated will outweigh the extra cost. Lastly, always be mindful of the unit of measure. Marginal cost is always expressed as the cost per unit. Now that we have covered the core principles and the application, let us move on to the final slide, where we will discuss some common mistakes to avoid to ensure your calculations are always accurate. Common mistakes to avoid. Now that we have walked through the practical example, let us conclude by discussing some common mistakes to avoid so that you can ensure full marks in your assessments. First, be very careful not to confuse average cost with marginal cost. A common error beginners make is simply dividing the total cost function, C of x, by x. Please remember that this calculation gives you the average cost, not the marginal cost. As we have established throughout this lesson, finding the marginal cost strictly requires differentiation, which we denote as dc over dx. Secondly, do not ignore the constant term when you begin your differentiation. If you look back at the example we just solved, we had a fixed cost of 5,000. It is vital to remember that the derivative of any constant value is always 0. Ensure that these fixed costs do not accidentally carry over into your final marginal cost formula. Finally, pay close attention to your application of the power rule. When you are differentiating terms such as x squared, as we did in our illustrative example, ensure that you bring the exponent down as a multiplier and reduce the new power by 1. Precision in this step is key to arriving at the correct derivative.